In this lesson, we'll look at linear equations in two variables. Let's start with the standard form of a linear equation. That is ax plus by equals c. Here, the term linear means that both the x and the y variables are raised to the first power, and the first power alone. The a, the b, and the c are real numbers, and a and b are not both 0. In other words, one of the a or the b could be 0, but not both. One of the central topics to study when looking at linear equations is slope. The slope of the line passing through the points x1, y1, and x2, y2 is m equals y2 minus y1 over x2 minus x1. Sometimes you'll see this abbreviated using the symbol delta. It's a Greek letter that stands for change, and you'll see delta y over delta x. That means that the slope is equal to the change in the y's divided by the change in the x's. Now this formula for slope works provided the denominator x2 minus x1 is not equal to 0. This is because you cannot divide by 0, and so we say that lines have slope when x2 minus x1 is not equal to 0. That is equivalent to saying that x2 is not equal to x1. So as long as the two x values are different, we can compute the slope. Now there's another formulation for slope that you may remember from high school, and that is rise over run. One way to think about rise over run is to have a line and start at a point, and then you rise a certain number, and that's rise up, and then you run to the right. Some people get confused with slope when the slope is a negative. Let me show you a trick that you can use every time to prevent getting confused with negative slope. If instead of thinking of a negative slope as rise, think of a negative slope as fall over run. And in that case, you would have a line where you start at a point, and then you fall a certain number, and then you run. Notice the similarities between the graph on the left and the graph on the right. You always run to the right. And then the negative is handled in the numerator. You either rise if the slope is positive, or you fall if the slope is negative. In example 1, find the slope of the line that passes through the points -2, 1, and 6, 5. So let's write the slope formula. M is equal to y2 minus y1 over x2 minus x1. I'll use the point -2, 1 as the first point, and 6, 5 as the second point. You must use the points in a consistent order, so I suggest that you label the points when you use them. y2 is 5, minus y1 is 1, over x2 is 6, minus x1 is -2. 5 minus 1 is 4. 6 minus -2 is 8. So we have 4 over 8, and that simplifies to 1/2. In example 2, find the slope of the line that passes through the points -5, 7 and -3, comma 7. So again, I'll label my points 1 and 2. I'll write out the formula for slope. M is equal to y2 minus y1 over x2 minus x1. This is equal to 7 minus 7 over negative 3 minus negative 5. 7 minus 7 is 0. Negative 3 minus negative 5 is positive 2. And then 0 divided by 2 is 0. So this one works out, and the slope is 0. Let's look at example 3. Find the slope of the line that passes through the points 2, 8 and 2, 0. If we try to compute the slope, we would have m is equal to y2 minus y1 over x2 minus x1. And that would give me 0 minus 8 over 2 minus 2. Notice that this is going to give us a 0 in the denominator. This was one of the provisions from the slope definition. You cannot have 0 in the denominator. Therefore, we say that this slope is undefined. Let's classify the slopes in 4 different ways. First, we have positive slope. Remember, that corresponds to rise over run. We have a graph that is increasing from left to right, and that is when the slope is positive. In other words, m is greater than 0. On the right, we have negative slope. Negative slope means we have a line that is decreasing from left to right, and that would be m is less than 0. We can also have 0 slope, as in example 2. A line with 0 slope is a horizontal line. Finally, a line with undefined slope is a vertical line. Now notice where the horizontal line and the vertical line come from with respect to the slope formula. On a horizontal line, all of the y values for every point on the line are the same. So in the numerator of the slope formula, you have y minus y, which is 0. For the undefined slope, that results in a vertical line, and all of the x's are the same. So in the denominator, you get x minus x, which is 0, leading us to an undefined slope. Now there is one term that is somewhat ambiguous, and we will not use it in this class, and that is the term no slope. Some people define no slope to be the 0 slope, resulting in a horizontal line, and some people define no slope to be undefined slope, the vertical line. Because of this confusion, we will not use this term at all. One way to write the equation for a linear equation is called the slope-intercept form. That format is y equals mx plus b, where the x and the y are variables. The m stands for the slope of the line, and the b stands for the y-intercept of the line. In example 4, given y is equal to 3x minus 4, find the slope and the y-intercept, then graph. So if we look at the equation, y equals 3x minus 4, we can read off the slope. That is the number in front of the x. So slope is equal to 3. And we can read off the y-intercept. The y-intercept is the b, and it's equal to negative 4. Don't forget to use the negative with the negative 4. And remember that slope is just the number in front of the x. It does not include the x itself. Finally, we want to make the graph y equals 3x minus 4. To do this, start with the y-intercept at negative 4. Remember that the y-intercept is the point on the y-axis that the graph goes through. And then the slope is equal to 3. You can think of that as 3 over 1, which gives us the rise over run. So from 4, we're going to go up 3, 2, 3, and then over 1, and then up 3, 1, 2, 3, and over 1, run 1. And we continue doing this, 1, 2, 3, over 1, 1, 2, 3, over 1. And then draw the line through those dots. And then use arrows to indicate that the line goes on forever. Notice that the slope is positive 3, which would indicate that the line rises or increases from left to right. Let's look at example 5. Find the equation of the line with slope negative 2/3 passing through the point negative 1, 7, write in slope-intercept form. So let me write down what we have. We have a slope is equal to negative 2/3, and we have a point negative 1, 7. To find the equation of this line, I'm going to use the slope-intercept form. Y equals mx plus b. We know m is negative 2/3. And we have a value for x and y. So I'm going to plug in the point values, x is equal to negative 1 and y equals 7, into the equation. And the only variable that's left from the y equals mx plus b equation is the b. We can use this equation to solve for b. So first, let's simplify. We have 7 is equal to positive 2/3 plus b. I'm going to multiply both sides by the least common denominator. That's 3. That gives me 3 times 7 is equal to 3 times 2/3 plus b. 3 times 7 is 21. Distributing the 3 on the right side, we get 2 plus 3b. Moving the 2 to the left, 21 minus 2 is 19. That's equal to 3b. And then divide both sides by 3 gives us b is equal to 19 over 3. The question asks for the result to be in slope-intercept form, so we write y equals the slope, negative 2/3, x plus the y-intercept, 19 over 3. Let's look at example 6. Example 6 says, find the equation of the line graphed below, write in slope-intercept form. So first, we notice that we have 2 points marked on the graph. Let's identify those points. So this first point is negative 2, 4. And the second point is 6, negative 2. So using these points, we can find the slope of the line. So m is equal to delta y over delta x is equal to negative 2 minus 4 over 6 minus negative 2. That's equal to negative 6 on the top and positive 8 on the bottom. That reduces to negative 3/4. Next, to create the equation, again, we'll use y equals mx plus b. We need to plug in the slope of negative 3/4. And we need to plug in values for x and y. We have 2 different points, and it does not matter which point we plug in. We can plug in either point. I will plug in the first point. So y is 4, and x is negative 2. To solve this equation, we can multiply by the least common denominator. I'll use the denominator there, which is a 4. That gives me 16 is equal to 6 plus 4b. Moving the 6 to the left-hand side, we get 10 is equal to 4b. And then divide both sides by 4. b is equal to 10 divided by 4, and that reduces to 5 over 2. We can write the equation of the line as y equals the slope, negative 3 over 4 times x plus the y-intercept plus 5 over 2. If you go back to the graph, you can locate the y-intercept and notice that it is in fact 5 over 2. Let's look at example 7. Example 7 says, identify each graph shown with the linear equation on the right. So we have three equations, y equals 2x plus 1, y equals negative 2x plus 1, and y equals 4x plus 1. Notice that all three of these equations have the same y-intercept of 1, and that on the graph on the left, they all intersect at that point. So we cannot use the y-intercept to help us distinguish which graph is which. Notice next that the three graphs on the left, one of the graphs has a negative slope because it is decreasing from left to right. The graph with negative slope is F3. Looking at the equations on the right, we notice that only one equation has negative slope. And that is the equation y equals negative 2x plus 1. So that must be F3. Next, we need to distinguish between F1 and F2. Notice that F2 is steeper than F1. When a line is steeper than another line, that means it has a larger slope. So this tells me that the slope for F2 must be larger than the slope for F1. If we look at our two remaining equations, we have a slope of 2 and a slope of 4. The steeper slope is 4. So that tells me that F2 must be the equation y equals 4x plus 1, and that leaves F1 to be y equals 2x plus 1. Here we were able to use information about the slopes to distinguish between all three lines. The average rate of change is similar to slope in that it measures how a function changes over an interval. The difference is that the slope of a line is always constant for any 2 points on the line. We use average rate of change for any function, and thus the average rate of change can be different over different intervals. Let's look at this picture here. I'm going to graph a function, and I'm going to mark the endpoints x1 and x2. And let's call this function f. We're going to find the points on this graph above x1 and x2, and then we're going to mark their y values. Their y values are just the function values evaluated at each of those points. So the first one is f of x1, and the second one is f of x2. Next, I'm going to draw the secant line that goes between these 2 points. And then we're going to compute the slope of the secant line. So the secant line would be the y value from the second point, which is f of x2, minus the y value from the first point, f of x1, over the second x coordinate, x2, minus the first x coordinate, x1. That is the slope of the secant line. The slope of the secant line is what we call the average rate of change for the whole function. So average rate of change is equal to f of x2 minus f of x1 over x2 minus x1. So therefore, average rate of change is nothing more than slope between the line that is from 2 points on any function. It does not have to be a line that you start with. For example, number 8. The population of a colony of ants is given in the graph. Find the average rate of change from day 3 to day 10. So here we'll use the average rate of change formula with day 3 and day 10. The average rate of change is going to be the slope of the secant line that goes from the point that goes through day 3 and the point that goes through day 10. So here, average rate of change is going to be f of 10 minus f of 3 over 10 minus 3. Remember that f of 10 is going to give me the population at day 10, and f of 3 is going to give me the population at day 3. We will use the graph to read off these values. The population at day 10 was 1,280. The population at day 3 was 450. 10 minus 3 is 7. And when you compute this value, you get 118.57. We need to provide the units. Since the numerator calculates the population of ants, we'll use ants divided by, and then the denominator counts the number of days. We'll use days for the denominator. So the average rate of change is 118.57 ants per day. Finally, let's look at solving equations and inequalities graphically. Example 9. Solve 2x minus 5 is equal to negative x plus 4, and then solve 2x minus 5 is greater than negative x plus 4, and 2x minus 5 is less than negative x plus 4. We'll do this using the graph. First, let's solve 2x minus 5 equals negative x plus 4. So to use the graph to solve this, basically what we do is we assign y1 to be one side here. So y1 is going to be 2x minus 5, and we say y2 is equal to negative x plus 4. Notice that these are the two graphs that are listed on the left. This top one is y2 is equal to negative x plus 4. The bottom one is y1 is equal to 2x minus 5. I can tell which is which because of the slopes. The red line has a positive slope, so that must be 2x minus 5. The decreasing, the purple line, must be y equals negative x plus 4. Now 2x minus 5 is equal to negative x plus 4 when the two graphs intersect. So if I find the intersection point is 3, 1. Since the equation is written with x's, then we know that these two parts will be the same when x is equal to 3. So the intersection point gives us the solution for x to this equation. They're both, when we use x equals 3, equal to 1. Now to solve the inequality, 2x minus 5 is greater than negative x plus 4. We're going to look at the position of each function. Greater than means higher up on the graph. So 2x minus 5 is higher on the graph than negative x plus 4 for all of the values on the right side of x equals 3. So that would be x is greater than 3. And then the last inequality, 2x minus 5 is less than negative x plus 4. When is the graph of y equals 2x minus 5 lower than the graph of y equals negative x plus 4? That is on the left side of x equals 3.